All right, so the way that I was taught what we're going to do next, which is periodic trends, is that my chemistry teacher gave me a periodic table and said, memorize that these guys up in this corner are the biggest ones, the ones in that corner are the smallest ones, the ones in this position have the highest ionization energies, the ones in that. So they made me just memorize the patterns, but I was never really told why. And so we're going to take the opposite approach. I'm going to focus on the whys with you, and then the patterns will come organically out of that. Okay? So that's what this packet is going to primarily do, is explain the whys. All right? And we might have to grab coloring pencils for some of this. Maybe not necessarily today, but we'll see. All right? We're only going to do the front page and the first half of the back side of this first page. Just today. We'll do the rest of it next week. If you can master what's on this front page today, the rest of it will fall in line, because everything else is based on this concept that's on this first page. All right? So first of all, on the periodic table, what do we call rows? Periods. What about columns? What do we call those? Groups or families. All right, so let's take a look across a period. So, hang on, let me grab a little periodic table here and put it under the document can. So we see it. Oh, this little magnetic one. It's handy dandy. How is our periodic table arranged? Do you remember? What did Moseley do? He did it by atomic number, right? So, as I'm going across the period this way, right? What am I adding? I'm adding protons. Everything that you're going to learn in periodic trends has to do with magnets, magnetic attractions. All right, so what do you know about magnets? To get two magnets to stick to one another, what must they be? Opposite charges. If they're the same charges, what happens? They fall apart. They repel. All right. If you have to compare beryllium to lithium, who's a better positive magnet? How come? What? There's more what? There's more protons. So adding protons makes the nucleus a stronger positive magnet. Since positive charge will attract electrons, nuclei with greater protons will pull on those electrons more tightly. What do you think is going to happen to the radius if you can pull them in more tightly? It's going to have a smaller radius. So making the atoms smaller. Now, this concept of having more protons making you smaller is true so long as the atoms that you're comparing have the same number of, take a look at these pictures, what do they have the same number of? Shells, energy levels or shells. All right, so let's fill some of this in. So how many protons did lithium have? Let's look at that table again. No, you can't see that. Okay. You can't see that. How many lithium have? 3. So let's put a 3 here in the middle. 3p. How about nitrogen? 7. So I'll put a 7p here in the middle. And what about neon? 10. We're going to draw an arrow. Which one of these is going to be able to take its electrons and pull it in better? Neon. So we're going to draw a wide, wide arrow. Actually, let's do it over here. So these electrons are being pulled. They're being pulled inward. So a wide arrow being pulled inward. The electron that's in that outermost ring is being pulled inward. Unfortunately, that picture's just so tiny that I can't get the arrow in there. And then over here, what can we say about that inward force? It's less, so I'm going to draw just a thin little arrow going in, and there's the electron that's on the ring. And what about in nitrogen? It's kind of in the middle, so we'll draw it like an intermediate sized arrow. Not as fat as the neon one, not as thin as the lithium one. Okay. Okay, so over here it says the arrow represents the pulling force that the protons in the nucleus exert on the surrounding electrons. The wider the arrow, the stronger the force. Good. So that's the trend that we see as we look left to right, within one row. Okay? Let's talk about the trend that we see as we look down a column. So down a column is next. So we're going to look now at lithium, sodium, and potassium. So down a column. So let's start with this first bullet here. It says, adding energy levels on atoms is like putting on layers of clothes in the wintertime. The more layers you put on, the fatter you look. Okay, so take a look. What happens to the radius of lithium, sodium, potassium? It increases. Why? Because you have more energy levels. All right? So let's go back. Now, the problem is, it's not just a matter of putting on more layers. All right? It has to do with the fact that every time that I add another layer to this, that ring blocks the nucleus. All right? So adding energy levels blocks the pulling force of the nucleus. All right? And this is where I'm going to start using two colors. All right, so what do we say happens in lithium? You have these three protons, and what are these three protons doing? To that electron out here, what are they doing? They're pulling it in, and that's an electron. What's in this ring that I put in the middle? What's here? Here in that ring, what's in there? No, on that first ring. The nucleus is here in the middle. What's in that ring? That's an electron. What do electrons do to each other? Repel. So I'm going to draw an arrow pushing out. Do we have a tug of war taking place here? As the nucleus is pulling in, the electron is pushing out. All right, so let's take a look at sodium. All right, so the electron's being pulled in sodium. How many layers do I have now pushing out? Do I have two layers pushing out? Right? The electrons in the first layer are pushing out. The electrons in the second layer are also pushing out. They are too. I just didn't draw it. They're pushing on each other. Everything's being pulled in, but the problem is that now, by adding all these extra layers, you also have more repulsive forces taking place too. All right? Okay, what about in potassium? You have electrons being pulled in by the nucleus, but now you've got three layers of electrons that are pushing out. So, over here, right? So the black arrow represents the pulling force that protons in the nucleus exert on the surrounding electrons. The pink arrow, or whatever color you're using, and if you don't have another color, you could always draw the arrows pointing out as dashed lines instead, represents the pushing force that electrons in the core layers exert on the surrounding electrons. So what do you think determines radius? No. Is it maybe like the sum of the forces? So the radius is determined by the sum of these pulling and pushing forces. So let's go back up to the bullet points. This is adding energy levels blocks the pulling force of the nucleus. What do I mean by block? It means that when you add those extra core layers of electrons, and by the way, if you remember when we were talking about Bohr's model of the atom, the different layers have different names, right? So all the layers that are inside are called core. What do we call the outermost layer? We call it valence. You have to know the difference between the two. So this here is core, this here's core, that here's core, that last one is valence. In this case, this would be core, that would be valence, and here this is core, that's valence. So how many core layers does this have? One core versus sodium. How many does sodium have? 2 core versus potassium, which has 3 core. All right. When you add core layers of electrons, these additional core layers push or repel the electrons in the valence shell further, and they counteract the pull on that valence shell by the protons. So those core layers are pushing, and they're basically diminishing the effect of the pull by the nucleus. Does that kind of make sense? So in a sense, those additional core layers block the nucleus. The blocking of the nucleus is something called a shielding effect. All right, so the more shielding we have, the greater the atomic radius. So it's not just a matter of the fact that you're just adding more layers and voila, you look fatter. It's that these layers are doing something, and those layers are blocking the nucleus, and they're keeping that nucleus from pulling things in. So it's just letting things go out instead. Yeah, Michael. Yeah, but we're not talking about giving these atoms energy. This is in their ground state when they're doing this. All right? Okay, so let's talk about then where the largest atoms are. Okay? So based on this, where are the largest atoms on the periodic table? On the left or on the right? On the left. According to this, where are the largest of the atoms? On the top or on the bottom? Bottom. So the largest atoms are on the bottom left of the periodic table. Because not only on the bottom they have more rings, but they also have more protons pulling in. Okay? Bottom left. So the biggest of the atoms, what would it be? Francium. All right? How about the smallest ones? If we're looking left to right across the period, where are the smallest ones? Are on the left or on the right? On the right. And then if we look at down a family, are they on the top or are they on the bottom? On the top. So the smallest atoms are on the top right. All right, so Victor told us that francium was probably the biggest one on the periodic table. What would the smallest element on the periodic table be? Helium. Yes, sir. But they have a lot of protons, so even though they have a lot of layers that are pushing out, all the extra protons that you put in the middle are helping to pull in. So it's all a tug-of-war between pulling and pushing forces. Okay? All right. This concept here, really critical for next week. All right? So I need you to, if you have questions, ask them now. Get this memorized because it's going to take some effect next week. All right, now, let's look at the back. Just the top part. Okay. Okay, so that island of stability video, we were talking about core, like shells, right? And what did we determine happens to things that have incomplete shells? Are they stable? No. So atoms with incomplete outer layers, or what we call valence shells, are unstable. I mistyped something. There's a typo there. atoms form ions in order to become stable. So in nature, most elements don't exist as atoms. They really exist as ions because most things don't have full valence shells. The only exception to that are the noble gases. They already come out of the sun with full valence shells. But everything else doesn't. And so in nature, it'll exist as an ion. What do elements have to do in order to form an ion? They have to either gain or lose electrons. And this is just some vocab. What's a cation? What kind of charge does it have? Positive. And the way you remember it is that the word cation has a T in the middle. The T looks like a plus sign, right? How do you form a cation? You have to lose an electron from the atom. So electrons must be lost from the atom. So say I have lithium right here. So lithium has 3 electrons in it, right? Is it stable? No. This is unstable. The atom is unstable. How come? It only has 1 little electron in the outermost layer. How many does it really want? Most atoms want to have 8. If you're in the first period, however, it's not 8, it's how many? Think about the elements in the first period. All they have is an s orbital. How many electrons can you put in an s orbital? 2. In the second period, you have an s orbital and a p orbital. How many total electrons do you put in those 2? 8. The same thing would be true if you're in the third period. If you have an s orbital and a p orbital, you want to have 8. If you have an s orbital, a p orbital, and a d orbital, you want to have 18. Okay? All right, so this is unstable. It only has 1 electron, but it really wants to have 8. So in nature, it's not going to stay that way. What's it going to do? It's going to give its electron away. So that outermost layer goes bye-bye, it disappears, and it uncovers the layer underneath that's totally full. Right? Because that's an s orbital, and it's full because it only needs 2 electrons. All right, so when electrons are lost from the valence shell, the radius of the resulting ion is decreased. It's like taking off your winter coat. Once you remove it, you appear thinner. What about an anion? What kind of a charge does that have? Negative charge. To form an ion, what must you do? Gain electrons. When electrons are added to the valence shell, right? So in this particular case, oxygen. Take a look at oxygen. How many electrons does it have right now? No, count it. 1, 2, 3, 4, 5, 6. What does it really want? Now, is it stable in this, looking like this? No, this is unstable. Oxygen has one of 2 choices. It could either choose to lose those 6 electrons or gain 2 more. What's easier to do? Gain 2 more. All right, so when you gain those 2 electrons here, and I put them in here in gray, right? Adding those 2 electrons, look at what happens to the radius. What happens? Makes it get bigger. So when electrons are added to the valence shell of the radius, the resulting ion is larger. Or the shell, right? The radius is bigger. Why? Because when you put those electrons in there and you put them next to another electron, what kind of charges do they have? Negative charges. So what is one negative thing going to do to another negative thing? It's going to push on it. This electron that you added is going to push on that electron. And it's going to push on that one. And it's going to push on that one. And it's going to push on that one and that one and that one and that one. And so will this other guy. It's going to keep pushing and pushing and pushing and pushing and pushing. Right? And those added electrons repel the electrons that were already there, and it makes that sucker swell out in size. All right? Sound good?